so in this system, so in the last lecture, we talked about finding the principal stresses in 3 dimensions. So we know we can use this cubic equation here to determine our 3 principal stresses, sigma P1, sigma P2, and sigma P3. Um, so we know that for equivalent states of stress, they're going to have the same principal stresses. So what I mean by that is if we have a stress in the x, y, and z coordinate system and we transform it to a state of stress in the um, x prime, y prime, and z prime coordinate system, the principal stresses within the x prime, x, y, z coordinate system and the x prime, y prime, and z coordinate systems are going to be the same. So, um, so in order for that to be true, the coefficients of this cubic equation, which I'm going to highlight in yellow, right? These 3 coefficients here have to be the same. Okay, so our first coefficient will be I1. Our second coefficient is going to be I2. Then our third coefficient is going to be I3. Okay, so what you can do is that since you know that the principal stresses must be equal in both for the x, y, z and the x prime, y prime, and z prime condition, you can see if they're invariant to check if you perform your transform correctly. You can see if your stress invariants are equivalent. If your stress invariants are equivalent, that means that they have the same principal stresses, and it means that your transformation was at least to an equivalent state of stress, if not at least probably correct. So, um, so, um, so please use the stress invariance to check yourself when you do a stress transformation. Also, when you're finding the principal stresses, after you solve it, your stress invariance of your principal stress from your principal stresses should be equivalent to I1, I2, and I3. Okay, so um, so in this example problem, what we're going to look at here is we have one state of stress that was transformed from the xyz state of stress to the x prime, y prime, z prime coordinate system here, and we want to confirm that the stress invariants in the original state of stress and the final state of stress are equivalent. So we have, um, so let's just calculate I1 for both of these, for the xy coordinate and for xyz and for the xy, x prime, y prime, and z prime. So the one thing I will note is that this is a 2D case of plane stress. So since it's plane stress, sigma z, tau zx, and tau yz are all 0. So I1 is just going to be the sum of all the normal stresses. So in this case, for I, we have 3 in the x direction and 9 in the y direction. So we'll get 12. And for the I1 prime, we get 10 in the x plus 2 in the y, so that's also equal to 12. These are equal, so that's good. All right, we can do the same process for the second stress invariance, I2 and I2 prime. So if we do that, what we end up getting is we get I2 is equal to sigma x times sigma y minus, so we get 3 times 9 minus the square of our shear stress, which is equal to -4. So we get 27 minus 16, which is going to be equal to 11. For I2 prime, we're going to get the normal stresses times each other again. So we're going to get 10 times 2, and then our shear stress again, which was -3 squared. So what we end up getting is we get 20 minus 11. All right, and that's going to be equal to 9. All right. All right. Sorry, 20 minus, went ahead of myself here, sorry. So it should be 20 minus the square of 3 is 9, and then that would be equal to 11. Jeez. Okay. So that is your, so both the second stress invariants are equivalent. And then because we have all of these 0 terms, if we look at the third stress invariant equations, every term in all these stress invariant equations has either sigma zx, or it has tau zx, or tau yz. So all of these have basically going to be zeros. So all the terms are going to be zero for both the I3 prime and I3 case. So these are again equivalent. All right. So since I1 and I1 prime are the same, since I2 and I2 prime are the same, and since I3 and I3 prime are the same, we both of these states are equivalent, and our stress transformation was successful.